A giant wind turbine has a radius of 43.9 meters, operates where the average wind speed is 6.64 meters per second. The air density is 1.31 times 10, 1.31 kilograms per cubic meter. What is the maximum amount? So if you could stop that air dead, right, which you can't do, because otherwise the air would pile up somewhere, right? But if you could stop it, the energy available to it is given by this formula, right? Is 1/2 the area times the density times the velocity of the wind to the third. Okay. Now, the area, the frontal area of these things is circular because they sweep out a circle. They go in a circular path, right? So this ends up being 1/2 pi r squared, where this is our radius, right? Times the density of the air times the velocity of the wind to the third. So let's plug these numbers in. 1/2 pi 43.9 meters squared times our density, which is 1.31. Oops. That's just kilogram meters to the -3. So kilograms per cubic meter, right? And then that's times 6.64 raised to the third power. That's meters per second. Now check out these units, right? It's like, whoa. Somehow that's going to have to equal joules. And I don't know if we care about that, but let's figure that out. Okay, so 0.5 times pi times 43.9 squared times 1.31 times 6.64 raised to the third. And that's 1.16 times 10 to the 6th. To the 6th, and that is watts, right? Okay, what are the units here, though? This is going to be, that's meters squared, kilograms, meters to the -3, meters squared, seconds. Oh, wait, no, meters to the third, seconds to the -3. Is that right? Yeah, because this guy's meters, right? That's, okay. Somehow that's got to equal watts, right? We'll figure that out. All right, so now the question is, what power does it capture if the air exiting the turbine is still going 5.14? So it's just going to slow the air down a little bit, which is really what happens with a wind turbine, right? So now the power is going to be the 1/2 A rho V input, right, to the third, minus 1/2, the same area, the same density, we'll assume, right, V output, right, to the third, which ends up being 1/2 times pi times 43.9 squared times 1.31. And then I'm just going to do factor this factor out of both and just say that this is now 6.64 to the third minus 5.14 to the third. Okay. Which is nice because now I can just hit up arrow on my calculator. Let's put some parentheses in here. Minus 5.14 to the third. Okay, let's see, 5.14, let's do this. And this is 6.22 times 10 to the 5th watts, or 622 kilowatts. Either one is correct. So that'd be a more realistic figure. I mean, I don't have any idea, right? I just made up this number, but it's going to be, you know, less than the amount of energy available to it, right? Okay. Okay, if the electrical generator is 89% efficient, what electrical power does it create? So this is the energy captured by the plant, right? Or the per second, right? That's watts. So efficiency is output over input. So output is efficiency times input. And this power captured by the turbine part is what is the input for this electrical generator. And by the way, electrical generators are actually more efficient than this. In fact, some of them are like 99% efficient. I don't know what the ones are on wind turbines, but we can neglect almost that. But this one, this is a cheap one, Okay, so let's see. So we're going to go 0.89. 89% of this becomes electrical energy. And that is 6.22. It's 6.22449 times 10 to the 5th. So take that number and multiply by 0.89, and I get 554 kilowatts. What it says on my calculator is 5.5398 times 10 to the 5th watts. These are the same thing, right? All right. Wind power.